This is a presentation of the 19th Annual Colorado Snow and Avalanche Workshop, a program of the Colorado Avalanche Information Center, Friends of CAIC, and the National Avalanche Center, presented by DINAFIT and Pomoka.
Okay, hi everyone. My name is Kevin Hammonds. I'm assistant professor in the Civil Engineering Department and the director of the Sub-Zero Research Laboratory at Montana State University. It's a real honor and a pleasure to be able to present to you today at this virtual CSAW event. Thanks to all the organizers for putting this together. I'm going to be presenting to you today some ongoing research in my research group that's related to operationalizing LiDAR for avalanche forecasting. This research is sponsored by the Transportation Avalanche Research Pool, so big thanks to them for funding this research, and we hope to be able to continue to work on this with them in the future. Along those lines, I'd like to also start by going ahead and acknowledging the other collaborators we have on this project. So this is very much a multidisciplinary and collaborative research project with myself and my graduate student, James Dillon, working from within the Civil Engineering Department at MSU. We're primarily working on the laboratory and field LiDAR measurements. We also have Dr. Sean Yaw and Peter Otson from the Computer Science Department that are taking on the software and algorithm development component of the research, and then also Dr. Joe Shaw and his graduate student Nathan Field from the Electrical Engineering Department, who have been our LiDAR expert consults more or less throughout this research project. So big thanks to all my collaborators as well. Okay, so let's start off by just talking a little bit about what is LiDAR. So from the traditional sense, LiDAR, meaning light detection and ranging, is a remote sensing tool that uses light waves, you can think of them as lasers, to retrieve the target position or the distance of that target from the LiDAR unit. And it can do this with a really high degree of precision. So what's really happening, if you want to think about it in a cartoon sort of sense, is that you're sending out a pulse of energy from your LiDAR. It's bouncing off some sort of target, and it's coming back to you. And that tells you something about how long that it took for the signal to move from one place to the other and back. And that basically tells you how far away that target is. So this technique and this instrument is used quite heavily throughout the geosciences, depending on how precise and what kind of sampling rate you want and what kind of power you need from the LiDAR. These things have been implemented on many different types of platforms for different applications. A few examples, there's the NASA ICESat satellite that has a LiDAR on board that was measuring the surface height for sea ice and ice sheets in the Arctic and Antarctic. There's a current mission called the NASA ASO mission that has put LiDAR on an aerial platform, and it's scanning while flying, measuring snow depth for hydrological forecasting applications. And then there's the ground-based platforms. This is what we're going to focus on, what we're using in our research, where you just leave the LiDAR at a static location on the ground, and you use it to scan, in this case, this avalanche terrain behind our LiDAR. You use it to scan that terrain, and then that is your LiDAR data that you're going to analyze. These things are called terrestrial laser scanners commonly, or TLS for short. So some previous LiDAR avalanche forecasting applications that you may have seen, particularly if you've been to CSAW in the past. Jeff Deems has done some excellent and foundational work and given some good talks on this at CSAW, where he was able to use a LiDAR instrument very similar to ours to map the start zone snow depth at a basin in an effort to help provide a better tool for implementing avalanche mitigation structures or mechanisms. So on the left is an image from a basin, on the right is what the LiDAR image looks like in a different zone after an avalanche had occurred. Another study that was recently presented at the ISSW in 2018 was a study from Svalbard where they were using similar LiDAR for characterizing the development of cornice and cornice failures on a ridgetop, shown here. And these studies and others like them have been using LiDAR in the very traditional sense, mapping snow depth as a function of the LiDAR target location, and that gives you some really useful information for avalanche forecasting to know how deep the snow is. So our approach is just subtly different in that we want to be able to do that because it's really important to be able to know the snow depth, but we also want to know what else can we learn from the snow. And this is based on the idea that if you're measuring the properties of the scattered light that's coming back from the material, back from your material, in this case snow, you must also be measuring something about the material properties. This is a very commonly used approach for other materials characterization techniques like micro CT, where you're passing energy through a material, or scanning electron microscopy, where you're collecting electrons off of the surface of the material. So using can we use LiDAR as a probe is kind of the question here. Can we characterize something? Can we learn something about the snow beyond the snow depth, like the grain size, the grain shape, the density of the snow, so on and so forth? So just to further illustrate this point, or kind of better define the question, you could think about snow as a porous medium, as is shown here, and you could think of the incoming light that's shown incident on this snow surface as your light emitted from your LiDAR. And what happens, interestingly, when it interacts with something like snow, is it doesn't just, all that light just doesn't bounce back towards your LiDAR. It actually scatters in multiple directions. Some gets lost in the snow, some gets absorbed by the ice grains. So you only get some fraction of that incident light back, and that's called the return intensity. And it's this return intensity that's essentially our only measurement that we're going to be able to try to make use of. So the question is, can we learn something more about the snow as a function of this return intensity? As just a quick example that sort of supports this idea moving forward is if we look at some of this, again, this is the ridge terrain from the Yellowstone Club that was shown in the previous picture. If we look at it on 2 different days, the return intensity where you have the dark red as high intensity and sort of white as low intensity, on a fresh snow day, you get very high return intensity. You see that all across the ridge. But on a day where it hasn't snowed in a while and you've got very old snow and it's a relatively warm day, you get very low return intensities. So immediately what we found is, from our field data collection, is that there's something going on here with return intensity with regard to the snow type that you have out in the mountains. So that's the kind of thing that we wanted to try and exploit in this research as well. So to just more formally define our primary goal for this research, again, this is funded on behalf of the Department of Transportation Avalanche Research Pool. So we were really out to provide avalanche forecasters in this very operational setting with a real-time data product for processing LiDAR that can be used operationally and includes novel estimates of snow properties beyond snow depth. So we want to have this capability. We want to provide these forecasters the capability to collect LiDAR data and analyze it basically all from the comfort of their truck out in the field and have them looking at the data in just minutes. So 2-prong approach to achieving this goal. The first thing we needed to do was develop this real-time data analytics software. So we want to go from the LiDAR to your laptop to some visualization and software platform where you can look at that data in a variety of ways that might be useful to you for making avalanche forecasting decisions. And that's what Shanya and Peter Otzen have been working primarily on from the computer science department. And the second part of the study in determining whether or not we can extract some novel information from the snow surface properties from the LiDAR data, we conducted a very thorough laboratory study, still in progress as well, where we're creating our own snow in the lab of different types and different densities, different grain sizes, different shapes. And we're characterizing it with the same LiDAR that we use in the field, except we're doing it from the laboratory. And then we're analyzing that data to see what kind of relationships might be there that are going to be of use to us for applying this eventually to the software product. So just real quickly, again, I'm going to kind of show you this picture from the Yellowstone Club. A big thanks to the Yellowstone Club Ski Patrol for always being very accommodating and working with us whenever we wanted to go up there. So this is kind of our primary field site where we're looking at this avalanche-prone terrain. Again, if we just look at this in terms of return intensity, you have some very obvious features that jump out, like this cliff band. Is this cliff band up here? That's pretty obvious to see. The trees in this zone are the trees up here, pretty obvious to see. But what's interesting is that where an avalanche had run, you can see the difference in that bed surface return intensity versus the chute right next to it where there was no avalanche. Has a very different return intensity. So these are the kind of things that we want to look more closely into with our laboratory research. I'm really happy and pleased to report the results from some of our laboratory research show that when we plot snow density, so as we change the snow density in the lab and look at it in terms of the average return intensity shown over here on the y-axis, what we saw and what we found is a very nonlinear but somewhat continuous relationship between the snow density and average return intensity as a function of several different types of snow grains. So whether it's rounded grains, refrozen melt forms, precipitation particles, they all seem to fit on this logarithmic line here. And that's exactly what we were not necessarily expecting to see, but hoping to see something like this. We also looked at the similar data for specific surface area, for snow grain size, and nothing quite nice came out of that data compared to snow density. So it would appear that snow density is going to be useful as far as a variable that we can exploit for our LiDAR application. What does the software interface look like that I'm saying is going to be very user-friendly? So on the left here is kind of what the window will look like on your laptop whenever you're plotting the LiDAR data after you've collected it. Again, this image here from the LiDAR data is just the Yellowstone Ridge terrain is shown here. And on the left here, just to orient you, I'll blow this window up here in a second. On the left, just to orient you, are all the controls so that you can load the data. You have a button for finding vegetation, and you plot all that up right here. And then you can choose which layer you want to look at. So you don't just have to look at whatever your surface scan was compared to the ground. You can also look at your surface scan compared to the weeks prior LiDAR scan or the one even before that. So I think this is going to be one of the kind of neat tools that is going to be available in this user interface. And then the more detailed info, if you want to know exactly at any given pixel in this image, exactly what the snow depth was, or any of the other variables that we'll plot, you can look at it down here in the printout of the window. So let's just zoom in and look at this image that's been generated. So this is looking at a new snow scan and comparing it to a previous snow scan. So the color bar here for snow depth is, dark red is increases in snow depth, white is essentially no change in snow depth from the previous scan, and then blue is decreases in snow depth. And that's really, I think, going to be an interesting and useful tool for the avalanche forecaster in that you can not just see how deep the snow is, but you can also see on any given day where you had more, say, wind loading, where you had increases in snow depth, versus wind scouring, where you had decreases in snow depth. Another interesting feature that you can use in this software platform is if you are just interested in, say, what's happening in detail around this sort of start zone, or this start zone, or maybe just down here, like how deep is this debris pile, you can just draw, you click a button and you draw any arbitrary shape around that region, and then that information in terms of the snow depth, average snow depth, the maximum snow depth, or density will be printed out here in this window as well. So that's just a quick overview of what the software user interface is going to look like. What I'm really excited about at this point in the research is that I think we're on the path towards not just to provide things like snow depth to the forecaster, which is remains an important parameter, important thing to know, but also I think we're going to be able, with just the toggle of a switch basically in our visualization software, you could also just look at this in terms of slope. So you might want to know whether or not the slope is changing towards the run out of your track, where you might have debris that's been piling up, or maybe you've got cornice developing near the top where you're getting a steeper slope. You'll be able to actually see that on a very fine scale with this sort of approach. You can also plot that up in terms of aspect. So if you're getting changes in aspect or slope, you can see that as well. I think this is going to be useful in terms of being able to see where you might have pillows of snow that have developed, where you get change in perhaps both slope and aspect in your start zones. But again, I think the combination of things are going to be the most useful. It comes from what we're deriving from the return intensity in terms of plotting the surface snow density. So the combination of being able to know what your surface snow density is with what the snow depth is in the same location, I think is going to be a really powerful tool for avalanche forecasters, in that you'll be able to see not just how much snow you have in a certain start zone or track, but also how dense is it. And that is going to be able to speak towards whether or not you have fluffy, low density powder snow that doesn't make a really cohesive slab, or whether you have heavily wind affected snow that would present a more dangerous situation where you have a really dense snow slab that can also be potentially very deep in your starting zone. And that is the sort of thing that will dictate or help shed some light on what type of avalanche forecasting or mitigation decision to make. So I think that's going to be sort of the more powerful thing to come out of this research. Again, this part is still ongoing, but we're hoping that within the next year, we're going to have this visualization software completely built, and laboratory and field experiments done as well, such that we can have this product available to all avalanche forecasters that have access to LiDAR. To conclude, I'm really happy to report that real-time LiDAR is on the verge of becoming a reality for avalanche forecasting. Personally, I find that really exciting, and I hope that you do too, that it's not just going to be something that scientists and researchers make use of or have access to, but if your Department of Transportation can acquire a LiDAR system, or your ski patrol can acquire a LiDAR system, this could perhaps be available to you as well. Again, I'd like to acknowledge my collaborators for all the hard work they put into this project, and again, the Transportation Avalanche Research Pool for their funding and hopefully for their continued support in supporting this project. Thanks. I look forward to hearing all of your questions.